All right, so let's jump right in. Today, we're tackling a really cool question. How in the world do scientists study memory in animals? I mean, how do you test something like remembering a specific place when your subject can't talk? It's a huge challenge, and it's led to some seriously clever experiments.
Seriously, think about it for a second. You can't just ask a mouse, hey, remember where you saw that cheese yesterday? Right? It's just not possible. So researchers had to figure out a way to actually see memory in action, to get objective, measurable proof without a single word being spoken. And that's the puzzle we're going to unpack today.
And the answer to that puzzle? Well, it looks something like this. This is the Barnes maze, and it is an incredibly elegant piece of scientific equipment. And lucky for us, this scientific poster is going to be our guide to breaking down exactly how this simple-looking platform becomes a powerful tool for looking inside the mind. So, what is it that we're actually testing here? Well, it all comes down to a concept called spatial learning. And trust me, understanding this is the key to seeing why the Barnes maze is so important for all kinds of research, from aging to brain injuries.
Spatial learning and memory is, pretty much what it sounds like. Think of it as your brain's built-in GPS. It's how you remember the way to work without even thinking about it, or how you can get around your own house in the middle of the night. It's this fundamental skill that we and a lot of other animals rely on every single day.
And that is the #1 job of the Barnes maze. Its entire design is focused on creating this controlled little world where scientists can watch spatial learning happen in real time. They can measure it, and they can see what different factors, maybe a new drug or a specific gene, might help it or, get in its way.
Okay, so to really get how this works, we first need to break down the setup itself. What are all the different parts of this clever puzzle? Let's take a look inside the arena. So, let's look at the design. What you're looking at is this big, open, circular table. And all along the edge, you can see a bunch of holes that all look exactly the same. But here's the trick. Almost all of them are dead ends. Only one single hole leads to a little hidden box, a safe, cozy escape for the mouse. For the mouse, the goal is pretty simple. Find that one escape hatch. See, mice are naturally motivated to get out of a bright, open space and find somewhere enclosed and dark. The maze just uses that natural instinct to drive the whole experiment. So, how does the mouse find the right hole if they all look identical? This is where the real genius of the setup comes in. The researchers put distinct visual cues, like a big triangle on one wall or a colorful poster on another, all around the room. The mouse has to learn to use these landmarks to figure out the location of that one special escape hole.
Now, this is a really key point. You might have heard of another memory test, the Morris Water Maze, where a mouse has to swim around in a pool of water to find a hidden platform. The Barnes maze, on the other hand, uses a dry platform and usually a bright light or a gentle fan as motivation, which is way less stressful for the animal. And why does that matter? Well, because really high stress can actually mess with learning and memory. So this design gives us a much clearer, cleaner look at cognitive ability.
Now, a test like this isn't something you just do once. It's not like you throw a mouse in there and call it a day. No, it follows a very specific 3-step training protocol to carefully build and then test the mouse's memory.
So this whole process is broken down into 3 main stages. First up is habituation. Then you move on to the acquisition trials. And finally, you have the probe test. Each of these steps plays a really important role in the overall experiment.
Okay, step 1, habituation. This is basically just an orientation session. The researcher puts the mouse on the platform and gently guides it over to the escape hole, letting it check out the safe little box. This whole step is about removing the fear factor and just kind of showing the mouse, hey, this is the maze and this is where you want to go.
All right, next up are the acquisition trials. This is the real learning phase. The mouse gets placed in the middle of the maze, and now it has to find the escape hole all by itself. And they do this over and over, usually for a few days. With every trial, a healthy mouse should get faster and faster, making fewer mistakes, because it's starting to connect those visual cues around the room to the location of the goal.
And finally, we get to the probe test. This is the moment of truth. This is the real memory test. The escape box is actually removed, so now none of the holes lead to safety. The mouse is put on the platform for a little bit, and the scientists just watch. Where does it go? Does it head straight for where the hole used to be and spend most of its time searching right there? Because that is the sign of a strong, specific spatial memory.
So, after all that training and testing, what does the data really show us? Let's decode these results and see what a good memory actually looks like in this experiment. The difference is pretty incredible. Before training, a mouse is just kind of wandering around. It takes a long time to find the hole. Scientists call this high latency, and it pokes its head into a ton of wrong holes, which they count as errors. But after the training, it's a completely different story. The mouse moves with purpose, it finds the location way faster, that's low latency, and it makes way fewer errors, often going almost directly to the right spot.
So, this all brings us to a couple of really solid conclusions. First, the training clearly works. It dramatically reduces both the time it takes and the number of mistakes. And second, that probe test is the real key. It proves the mouse has actually retained the memory and lets researchers analyze its search strategy. It shows it's not just random guessing, it's a truly learned behavior.
Okay, so we've learned how a mouse learns to solve a maze. Pretty cool. But what's the big picture here? Why does this one very specific experiment actually matter for understanding our own brains?
Well, the big takeaway is this. The Barnes maze gives scientists a reliable, standardized tool. It lets researchers objectively measure how memory is formed. And maybe even more importantly, it lets them study what happens when that process gets messed up, whether it's from a disease like Alzheimer's, a potential new drug, or some kind of brain injury. It turns a fuzzy concept like memory into cold, hard data.
And that leaves us with this final, really powerful question. Every single thing we learn from a tool like the Barnes maze adds to our fundamental understanding of how our minds work. And if we can truly, deeply understand the mechanics of a healthy memory, just imagine what possibilities that opens up for learning how to repair it when it starts to break down. Thanks for watching.